Imagine for a moment the sheer complexity behind keeping a modern railway network running. Not just running, but running safely, reliably.
Yeah, it's immense.
It's so much more than just the trains, isn't it? You've got signals, power, communications,
Oh.
this whole intricate dance.
Exactly. Everything has to work together perfectly. Millions of people rely on it every day.
But what happens when, something goes wrong? Maybe a component fails quietly or a function glitches? Or worse, the connections between systems fail in ways you just didn't expect?
Those unexpected interactions are often the trickiest.
And making sure these systems meet their RAM's targets, reliability, availability, maintainability, and safety, that's a huge challenge. Especially now with all this interconnected tech.
It really is. The complexity keeps ramping up.
So we need smarter tools, right?
And that's exactly why we're diving into something called IFF MECA today.
IFF MECA, okay.
It stands for Interface and Functional Failure Mode Effects and Criticality Analysis. Bit of a mouthful, I know. But think of it as like a powerful new lens. It helps engineers get a really thorough handle on RAMs and safety, especially for complex systems like rail electrification.
Okay, so our mission for this deep dive then is to unpack how this IFF MECA goes beyond let's say, the traditional ways of doing safety analysis.
Precisely. We want to show you how it gives a clearer, fuller picture of potential failures, their impacts.
And ultimately helps build safer, more robust railways. Got it. Let's explore.
Great.
So before we jump into IFF MECA itself, maybe set the scene a bit. Why do we even need a new approach? I mean, railway standards demand rigorous RAMs and safety proof, right? That's not new.
No, not new at all. It's fundamental. But here's the thing. Many of the methods we've used for years, like classic FMEA failure modes and effects analysis, they're starting to struggle.
How so?
Well, for one, they often have a pretty narrow focus. They tend to look at failures mainly at the component level or maybe a subsystem.
Right, looking at the individual bricks, maybe?
Kind of, yeah.
Yeah.
And another big limitation is they usually assume only one thing fails at a time.
But reality isn't always that neat, is it?
Not at all. You can get multiple failures, cascading failures, things that old-style FMEA just doesn't handle well. And critically, they often miss the combined effects of failures in interfaces, where systems connect, and failures in the core functions the system is supposed to perform.
So the gaps between the bricks, or maybe what the wall is supposed to do?
Exactly. And that oversight, it can leave hidden risks, unidentified defects lurking in the system.
Okay, that sounds serious.
It can be. Plus, these older methods struggle with complex dependencies between parts, and there's this mismatch. Traditional methods are often bottom-up, starting with components.
Like building with the bricks first.
Right. But more and more, contracts demand a top-down view. They want proof of overall system function and safety right from the start.
So the old tools aren't quite answering the new questions. You end up with maybe an inaccurate picture of RAMs, potentially higher costs, more hassle-proving safety.
You've got it. You really need that holistic view from the beginning.
Which brings us back to IFF MECA, the solution.
Well, it's designed to be that solution. It's a robust framework, a really flexible way to handle all these different aspects together.
Okay, break down that acronym again, IFF MECA.
Right. The IFF part interface and functional failure that focuses on the causes of failures. Are they in the interfaces, the functions, components, subsystems?
Got it. Looking for the source.
And the MECA part mode effects and criticality analysis, that's where you evaluate the effects of those failures on RAMs.
Cause and effect, basically, but integrated.
Exactly. And the advantages are pretty significant. You get a truly holistic view: system properties, functions, interfaces, components, their combinations, even external events.
Wow, okay.
And it offers that preferred top-down analysis, starting with the big picture functions and interfaces, but it can still pull in bottom-up details when needed.
That sounds incredibly useful. So it's not just finding risks. It sounds like it could actually help design better systems.
You hit the nail on the head. That's a major benefit. Early design flexibility. It lets you analyze whether a function is best done by hardware or software.
Wait, really? You can model that?
Yeah. You can even analyze swapping hardware for software, or the other way around, really early on. Think about finding a more cost-effective solution before you've built anything.
That could save a fortune.
Absolutely.
Yeah.
And it's designed for clarity. The assessments are visualized simply, concisely. Makes it easier for decision makers, even non-RAMS experts, to understand and manage the requirements.
Less jargon, more clarity. That's always good.
Right. We've seen it really simplify RAMS documentation, improve the quality, save resources, even help speed up getting approval from independent safety assessors.
And it plays nicely with standards like EN 50126.
Yep, fully supports them and maintains that traceability, which is crucial for modern contracts that focus on performance outcomes, functional tendering, they call it.
Okay, incredibly thorough. So
Yeah.
how does it actually work? What are the building blocks it uses to get that deep analysis?
Good question. It breaks the system down using some core concepts. First, you need a solid system description, just understanding how the system achieves its main goal.
Makes sense. Start with the basics.
And then you identify the primary functions, PFs. These are the big ones, the must-haves, usually tied directly to the contract. Non-negotiable functions.
Like the train must get power.
Exactly. Supporting those are the secondary functions, SSS. These are sub-functions. Now, if an SF fails, it might not stop the whole show immediately.
But it could lead to a PF failing later.
Precisely. Understanding that link is key for contractual RAMs. Then you have interfaces, ANs.
The connections we talked about.
Right. Physical links, communication flows, energy transfer, data exchange, any way different parts interact. It's not just about the wires.
So it's looking beyond the component itself at how it talks to everything else.
That's a great way to put it, because sometimes the weakness isn't the component, it's the handshake between components.
Okay.
And of course, you still look at components and subsystems, SSS, the individual parts, but IFF MECA sees them within that broader context of interfaces and functions.
More integrated.
Much more. It also helps with safety differentiation, clearly sorting out which functions are purely for safety, which are safety related, and which aren't. So you know exactly what impacts safety if it fails.
Crucial distinction.
And finally, a really neat feature is automatic SIL allocation. It helps quantify and classify safety integrity levels for functions based on failure probabilities.
SIL's safety integrity levels, that sounds important. Automating that classification.
Yeah, it takes some of the guesswork out, makes it faster, more consistent. It's a big help.
Okay, theory is great, but let's make it real. You mentioned rail electrification. Can we walk through an example?
Absolutely. Let's take a typical DC 750-volt traction power supply system, like you'd find in a metro or subway.
Okay, familiar territory for many listeners.
Its main job: get enough power to the trains, reliably, within the specified limits. Now, these systems are designed with a lot of redundancy built in.
For high availability, right.
It's exactly. Traction supply stations, TSSs, they have redundant switchgear, transformers, rectifiers, cable connections. And get this, one TSS is usually designed so it can still supply power even if the next one down the line completely fails.
Wow, so layers of backup.
Definitely. Key parts include the bulk supply station, BSS. That's where power comes in from the main grid, maybe at 33 kilovolts.
It's a main intake.
Right. Then you've got the cable ring, CR, providing redundant connections between the BSS and the various TSSs. The traction supply station, TSSS, steps down that high voltage AC to the 750 VDC the trains need.
Using transformers and rectifiers.
Yep. And finally, the third rail, TR, distributes that power along the track to the trains. It's usually segmented into zones, traction power zones, or TPZs, so you can switch sections on or off.
For maintenance or emergencies.
Exactly. And in this kind of system, IFF MECA would specifically identify functions like the supply of traction power and the train's power conversion as safety functions.
Okay, that paints a clear picture.
Yeah.
So now imagine I'm an engineer using IFF MECA on this system. I run the analysis. What kind of information does it actually spit out? What helps me make decisions?
Right, this is where it gets really practical. The output is like a detailed dashboard. You'll see the breakdown: subsystems, primary functions, secondary functions, what each part does.
The inventory.
Yep, and the external interfaces and components involved. Then it dives into potential problems. You get failure modes, how things can fail, loss of function, maybe a switch closes when it shouldn't.
And what could go wrong?
Exactly. And crucially, the frequency of failures, how often you might expect these things to happen. But it goes deeper. It specifically looks at the frequency of wrong side failures.
Wrong side failures, explain that.
Those are the failures that could directly harm someone. Like, imagine a maintenance worker needs a section of track power down. A wrong side failure would be the system incorrectly energizing that section while they're there.
Oh, okay. Directly safety critical failures.
Right. And the analysis quantifies the number of possible hazards from those failures.
How many ways could someone get hurt?
Essentially, yes. Then it calculates exposure probability. What's the chance someone is actually there when the hazard occurs? It considers things like maintenance frequency, how long tasks take.
So it's context aware.
Very. Then severity level. This categorizes the potential outcome: catastrophic, critical, marginal, insignificant. fatalities down to minor injuries. It forces a rigorous look at the real consequences.
So you're not just looking at the fault, but the whole chain reaction to the final potential impact.
That's the idea. All this feeds into the expected risk and overall calculated risk value, which then gets translated into a risk level.
Like a traffic light system, red, amber, green.
Sort of, yeah. Usually categories like intolerable, undesirable, tolerable, or negligible. It helps you prioritize using a standard risk matrix.
So?
And it flags the safety effect. Does this failure directly impact safety? Yes or no?
Clear answers.
And the safety level tells you if the risk is deemed acceptable, usually meaning it's tolerable or negligible, following that ELR principle as low as reasonably practicable.
ALR-LRP, right. Common in rail.
Very. It also identifies the specific safety-related function responsible and gives a clear hazard description, something concrete like evacuation in tunnel due to loss of traction power.
Making the risk tangible.
Exactly. And finally, you get the failure rate for that specific hazard, which is used to determine the required safety integrity level, SI.
Ah, SIL again. So the analysis tells you how robust your safety measures need to be.
Precisely. SISI 1 for relatively minor consequences up to SIL 4 for potentially catastrophic ones. Or it might say no safety-related if a SIL isn't needed for that function, based on the tolerable hazard rate, the THR.
Okay, that's a lot of interconnected information, but it sounds incredibly powerful for understanding and managing risk.
It really is designed to be comprehensive.
So wrapping this up, what's the big takeaway? For, the engineering students listening or the early career folks actually building these systems, or even just railway safety enthusiasts, what does IFF-MECA mean for them?
I think the core message is this. IFF-MECA offers this novel, combined way of looking at components, interfaces, and functions together. It really moves beyond the limits of older methods.
That top-down view, the flexibility.
Exactly, that top-down perspective, the ability to consider hardware versus software early on, its overall comprehensiveness. It makes it an incredibly valuable tool for today's complex railway systems.
Better quality, more transparency, less effort, improving RAM's compliance.
That's the goal. And often the result, it streamlines the whole process.
That idea of simulating hardware versus software swaps early on, that's fascinating. It lets engineers find the safest, most cost-effective solutions for the future right there in the analysis phase.
It opens up real possibilities for optimization.
So a final thought for our listeners, as you think about complex systems, not just railways, maybe power grids, autonomous vehicles, where else might these overlooked interfaces or functional dependencies be hiding risks? What stands out to you as the most impactful takeaway from this deep dive into IFF-MECA?